Hey viewers, in our last videos, we explored how a PN junction forms and how electrons and holes move across the depletion region. But what actually controls how easily those charge carriers move? That's what we are finding in today's video with the question, copper conducts better than silicon. Why? We will look at two quick examples, one with doped silicon and another comparing silicon and copper to see how carrier concentration and mobility together determine a material's conductivity. By the end, you will learn the equation that connects it all. It is the key to why semiconductor behaves so differently from metals. So are you ready? Let's dive in. Let's put that idea into action. I am taking these examples from IIT notes and the link is in the description. Also, I have put link of previous video in the description. If someone is interested, they can watch it from there. We will start with a simple example. Here you can see we have given a cylindrical piece of silicon which has diameter 1 millimeter and it is doped with phosphorus. This is free electron concentration. We have to find the length and the resistance is given 1 kilo ohm and we have given the electron mobility in silicon is this. So let's start. In the first step, we are going to compute conductivity. To compute conductivity, we know the charge on the electron. We have given this free electron concentration. We have given the mobility. We just introduced the conductivity equation and we substituted these values here to get our answer for conductivity. In the second step, we will find cross-sectional area. We know the formula to cross-sectional area. We have given diameter 1 millimeter in the example. And this is the value of pi. We find half of diameter is radius. Pi r square gives us the area of cylinder. Now we will use the basic resistance formula which I have already introduced in my previous video to find the length. Let's simplify it for the length. We know resistivity is the inverse of conductivity. So we have simplified it here. We already computed conductivity. We already computed area. We know from our example the resistance is 1 kilo ohm. Let's solve it for the length. So we find out silicon rod needs to be about 1.26 millimeter to have a resistance of 1 kilo ohm. This clearly shows silicon's low conductivity even when it is doped because its carrier concentration is much smaller than metals. Now, let us compare this with copper, which is one of the best conductors we use every day in wires and circuits. How much more mobile electrons present in the copper than in silicon, we will find out in this example. So we will calculate mobility. The charge on electron already we know. We have given the free electron concentration. We don't know the mobility. We are going to find out it. Here we assume the conductivity of copper is 5.96 into 10 power 7. Now you are wondering from where we took this value. So this is the standard value. You can find it in any textbook. We know the equation for conductivity. We simplify it. You can substitute sigma here for free electron concentration, for electron charge. So this is the final answer. So the electron mobility in copper is this. And this silicon electron mobility we have taken from the previous question. If we have to find out the ratio, we will divide these two, mobility, and this is the final ratio. Now, everyone is wondering, how can copper conduct better if its mobility is lower? Wait, we will see it. So, the secret is copper is huge carrier concentration, around 10 to the power 29 electrons per cubic meter, completely overwhelms its lower mobility. Silicon, even when doped, only have 10 to the power 20 carriers per cubic meter. So even though electrons move more easily in silicon, they are not enough to carry significant current. That's why metals like copper are excellent conductors and semiconductors like silicon are controllable, which are perfect to use in electronic applications. So what we have learned in today's video, both metals and semiconductor follow the same equation to find conductivity. Sorry, the mu is changed to m. You can correct it by yourself. In metals like copper, the free electrons are huge. In semiconductor, the free electrons are small, but mobility, it can change with doping, it can change with temperature, it can change with the field apply. So this balance between free electrons and mobility explains everything from resistance in silicon devices, why copper remain our daily life conductor. Thank you for watching the video and don't forget to subscribe, like and share my channel. Let's see you in the next video.